So this is work mostly with an undergraduate student of mine, Jingyao Zhu, who is finishing this year, and she's going to go work for Uncle's company in Silicon Valley for a year, and hopefully she'll come back to graduate school in astronomy or physics. But she's done a really fantastic job on this work, and we're using equation of state stuff from Frank Timmy's. Maybe this is something to skip over. You know, we've talked about whether we get enough in spiral, whether ejecting the envelope is a problem. So that's basically the context here. In terms of whether we can tap recombination energy, this has been suggested for some time as a possibility. And I want to highlight something here. We talk sometimes about the energy budget as if, for instance, that all the internal energy is available for use in moving material out of the envelope, and thermodynamically that's just not correct, because it requires that the envelope not only be ejected but also be cooled to absolute zero, right? So people argue about whether you should include the recombination energy in the budget. We should also argue about whether you should include the internal energy in the budget. It's really just a maximum, and so if you do something a little bit more careful, where you, for instance, consider the work that fluid elements do along their trajectories in an adiabatically expanding envelope, and you compare how much work is done with a correct equation of state versus what happens if you freeze the ionization fraction and the adiabatic index at the initial values. And you start with densities and temperatures at different points corresponding to a red giant model profile. You find that you can do almost 80 or 90% more work than you would if recombination energy weren't included, and the result depends strongly on what the initial entropy is. Because if you start off with a lot of entropy, then even if you expand to 10 to the minus 10 grams per cubic centimeter, you're still mostly ionized. And so you haven't really tapped any recombination energy. It's mainly for starting temperatures on the order of 30,000 K or so that you actually get to get something positive out of recombination. So it matters a great deal, not just as Natasha was saying, not just how much energy there is available, but where and when it gets released. So the big questions, of course. Is that energy lost to diffusion or convection, and does it happen in the right place? We've also talked about how the total amount of recombination energy that's available is a strong function of the initial mass, and it's mostly about low mass systems that we're talking about here. So the unambiguous argument from Noam Soker's group is that no, this cannot be tapped, and one of the main arguments here is that the timescale for convection or diffusion to remove energy from the recombination zone is less than the in-spiral time, and so they present, for example, for an AGB donor case, that convection is able to carry away most of the recombination energy, and then once, only at the very beginning is photon diffusion able to. We talked about Jason. I don't know your collaborator's first name. Emily Wilson and Jason Nordhaus did calculations similar, but with 1D models, but with a proper drag formalism for estimating the actual energy generation rate, and also found that the maximum possible convective luminosity is decently higher than the actual drag luminosity, so you would expect that convection could potentially carry away that energy. This, of course, is assuming that the envelope doesn't expand. You're basically working with the unperturbed donor profile, and it also assumes the validity of standard convection models. This is something else I wanted to highlight, is that when we're talking about convection and diffusion as being the possible ways that this energy could be removed, we have to consider that the convection model, mixing link theory, or any replacement for it in the context of hydrostatic stellar models, is not really applicable here. what we're really talking about is advecting flows that make a large-scale shear that may, in addition, have very small-scale turbulent eddies in them. And both of those processes, both that advection and that convection inside that flow, can act to transport energy. So, so really, even if you can show that convection can carry energy away, great, but it may be that advection is also able to. And Natasha has already summarized her argument pretty well, so I won't go into great detail here, but I also note that it's based, I mean, obviously these plots show just the equation of state, but the position of a stellar model on this equation, on these equation of state plots is based on hydrostatic stellar models, and in particular, the applicability of the maximum convective flux. So we're interested in trying to reproduce some of the results that Natasha and Jose did with double white dwarf formation, and in particular focusing on the following questions. How much does envelope expansion change the real fluxes compared to these 1D models? Do the shocks that are produced in, that's already? Wow, that's fast, okay. Okay, so do shocks prevent the effective use of recombination energy by keeping recombination from occurring, and can we carry that away? So we look at a model problem that's a 1.4 solar mass red giant and a 0.36 solar mass companion. We've spent a lot of time trying to develop a strategy for simulations where we carefully relax the initial conditions in an SPH code where nothing interesting happens. It's in co-rotation, and then map onto a 3D AMR code. There's our stellar model. It's a pretty garden variety red giant. And like others, we subtract a fraction of the interior profiles and make core particles. And we do that using a modified Lane-Emden equation. So here's our case I'm going to talk about. This is actually a low resolution case that she's completed, that Jingyao has completed. So we won't be able to explore all the questions that we want, but we are working on higher resolution versions. So as you can see, we can go several orbits now before Roche-Loeb overflow really starts, and before we get the initiation of common envelope, we get a disk structure that looks a lot like Ursula's, together with an initial shock that starts adding angular momentum to the envelope, and that drives a very rapid in spiral by about a factor of 17 in radius. And so that's the trajectories. This is the separation, and you notice that first there's a little bit of out spiral, which which you should not believe, because it actually turns out to be related to our core force calculation algorithm. But notice that if we include radiation diffusion or turn it off, it doesn't really change the final outcome very much. It changes a little bit how long it takes to initiate in spiral, but not the final outcome. This is sort of showing you the effect of the new and the old core force algorithms on the massive star case, which I'm also looking at. This is what I had in a conference proceedings paper from the IAU last year, and it turns out that that doesn't completely conserve momentum. So if I actually change the way I calculate forces on the core, I can tell you details in conversation, we get much less eccentricity in the in spiral, but similar in spirals. It really doesn't change the final result there, that we don't get enough in spiral to make binary black holes. As our a scatter plot of our system on top of the radiative efficiency factor from Natasha, and you see that our final model and actually our initial model are at pretty high entropy, and that's kind of what's keeping, that kind of keeps recombination energy from playing a big role. And if we look at where recombination is actually happening, it's actually in an adiabatically expanding region behind this primary shock, and doesn't progress very far, only to 10% or so in the case of hydrogen. Helium recombination is occurring pretty much in the same area. And so, so it's not clear that recombination is actually helping this very much at all, since this material is already on its way out, and that, and in particular, the material that's been shocked, it's a material that's been shocked already. You asked the question, where is the photosphere? It turns out it's probably outside of the box. In fact, what we've done here is to force the opacity to go to very small value at a density that is really comparable to the initial density at the photosphere in our model. And so you see that the only place where the flux limiter in our radiation solver tells us there's a photosphere is outside of the shocked region. So the region within which recombination is occurring is still optically thick, in agreement with what Natasha finds. So to summarize, and hopefully I cram it all in. Okay, so so these are preliminary results. Are low resolution, in particular, resolution at the surface where the temperature drops and you have recombination zones inside the primary, or say inside the donor in the initial conditions, are not well resolved yet. But so far what we've got is consistent with Nandes et al. Result for this 1.4 solar mass case. In spirals, as far as you can really believe at this resolution, if we include radiation diffusion, it does not materially change the outcome here, so sort of suggesting that radiation, in fact, does not act to carry things away. And recombination is occurring, and it is trapped, but it doesn't seem to be helping very much here. So our next steps, and we're hoping to get a paper out in the summer, is to do a 4x higher resolution and confirm the final separation. So thanks.
Yeah, so I mean, then you say that where recombination occurs, because what I see from my simulations, the recombination takes place within about 500 solar radii, right? So the bottom part of recombination, where you still have hydrogen fully recombined, is not unbound. The top one, 20%, yes, it's already unbound because it's already received recombination. So the definition, what you say as where recombination occurs is important, right? If you're talking about 20% up, yes, it's unbound, and it's the same as in my case, but it's the result of previous 80% to be recombined.
Mm-hmm. Yeah, so I mean, this kind of gets into how we're defining unbound gas. And as I pointed out at the beginning, you can't really count either the recombination energy or the thermal energy in the energy.
I'm speaking about the current position and only including the thermal energy, not including the potential recombination.
Right, but if you go zone by zone through your simulation or particle by particle through your simulation, you ask, okay, what's its energy? Is it positive?
Yeah.
And say that's unbound. That's what I'm saying. That's not necessarily correct, right? So the whole idea of positive energy corresponding to unbound really comes by analogy with the Kepler problems, right? Where you have an effective potential and you ask the question, where are the orbits not closed? They correspond to positive energies. Now, suppose you have particles that have internal energy. Do you just add it to the energies and say, okay, then they're more likely to be unbound? No, that doesn't work.
I understand that, but my question is that what you call as a recombination region, because in my case, the 500 solar radii, and I think it's about the same as in your case.
Let's see.
Do you start with 100% hydrogen ionized, or you start with 20%? What do you call as recombination region?
Oh, I'm just saying, where is the neutral fraction, not trivially small, or not trivially. Sorry, here we've got the neutral fraction. Yeah, exactly. Yeah, so neutral fraction here is between, it's of the order of a few percent, but inside the interior of the star, or inside this region here, it's basically zero.
Exactly. So it's a few percent. We're talking from different perspectives.
Okay.
I call it I start to count from when it's fully ionized. And this is where it works, not at the top when it's just partially ionized.
Okay, all right. I'm not sure I understand your question then, because we're counting from fully ionized as well, but.
So we have one more question.
But shown fraction.
Yeah, maybe we can.
But shown fraction is only up to 10%, and this is where I have already completely unbound gas.
Yeah, and this is.
Saying what is yours case, right?
Probably, and again, we haven't actually. I don't have a plot.
So 90% of your recombination energy has been released before, and you're not considering that when you analyze for whether it works.
Oh, at the base of the recombination region. Sure. Yeah. Okay. I guess. Anyway, I'm sorry. I don't understand the question. Maybe we can chat afterward.
Do you track helium recombination?
Yes, we do, and it's really happening in roughly the same place.
Can you quantify the?
Oh, the fraction that is?
How much help, as in what is being unbound or whatever the definition?
Oh, where is the, yeah, again, based on the positive energy criterion, where would it be unbound? I don't have a plot showing that, but I'm guessing that it's probably, well, actually, I don't know. Yeah, it's just, my statement about what seems to be unbound is just based on where the flow seems to be outgoing. Okay, sorry.
They're playing the thunder pool, how we come from. See? I know how it is.
It might be this one.
Yeah. This chip here. One, two. No, I, it's not like it, right?
So when it's you're below 25%, the future. So these are
Sure. So the problem is I don't really have.
So Jason, we'll talk next. Ready to 5-minute warning?
Yeah, that's fine. Okay, so I'm not really going to talk about recombination at all. What I'm going to talk about is convection in common envelopes, and we sort of came from this problem a little bit differently. So looking at the observations to start. And Ursula showed this, and Sylvia's done a lot of work on this, and what is really known, right? So if you look at sort of the distribution of white dwarf, M dwarf periods, you sort of get this. You get the bulk of these systems being below about a day period. So there's a very sharp cutoff where you don't sort of make these intermediate mass periods, you make very, very tight binaries. The other thing that we sort of know is that, so right away from the start of it, the efficiency of the interaction might be low, okay? So what do I mean by that? So different ways you can make the efficiency of the interaction low. One way is to take a lot of the energy and put it into a small amount of gas. That would make it a low efficiency, right? The other way is if you spread it all out, you might have actual sinks that carry energy away, and that would make the efficiency low too. But one of the things we have to do, I think, is create these short period binaries. The other thing to think about too is like, what are the physics in these systems, right? So right now, if you take sort of, in population synthesis codes, you take sort of these constant alpha prescriptions, even if they're low efficiency in some cases, they make this huge distribution of things that are longer of a day periods and have sort of some trouble down here. So they overpredict at the high end. But what do we know about stars, right? So we also know that RGB, AGB stars have very, very deep and very, very vigorous convective envelopes. So one of the things we probably should think about is what's the effect of convection in the systems. And you can do a very, very simple argument. There's nothing magic about this. It's probably the simplest argument I might have written down in a paper. But essentially, you can compare two timescales: the orbital decay timescale, the in-spiral timescale itself, and the convective transport timescale. And you can just ask the question which of those is larger. And so for a huge section of these systems, here's a 2 solar mass primary here. Anything that's shaded in yellow is the convective envelope. And okay, these are coming from 1D BESA models, but pick your stellar evolution model, it doesn't matter. You can identify sort of where the convective zones are. You can calculate these quantities out. And what you sort of see is that convection is operating much faster than the orbital decay should be. And so convection should be able to essentially take that energy, transport it up to the surface, and then radiate it away by photons. And so that could be the increase in luminosity you see as the companion starts to move through here. More massive stars, they have sort of multiple convective layers. Sometimes there's a disconnect between them. But you can definitely identify regions where that ratio flips and where in-spiral is then shorter compared to convection. And so it's thinking about it in some ways, it's sort of like putting a pot of water on the stove and turning up the heat, right? The water doesn't necessarily jump all the way up. When you do that, you make the convection more rigorous, and there's a larger heat flux to the surface, but you're sort of carrying stuff with you. Brian, Jones.
Sorry, I was just going to, so this is including the energy from the binary as a part of the budget?
Exactly, yes, not just, yep, so it's calculating that actually out as you do that. Okay, and so some of the assumptions we made here is, the first is that convection actually equally distributes the mass in each shell. So we're not putting necessarily a lot of the energy into a small amount of the mass. That may still turn out to be true, but I think you need simulations to actually see if that's true or not. So we made that assumption that mass in each layer is sort of equally distributed, the energy throughout. And then also, the other argument we made is very simple. If convection is operating faster than the in-spiral timescale, then we're just assuming all that energy is lost in the form of photons from the surface. And it's not until you get down to the bottom where that ratio flips, where then you then start using that energy to unbind the star. So the first thing you can do is you can calculate sort of where periods you should get out from these models. And I guess I should say here the crosses are where these companions would be tidally torn apart in the star anyway, so you can't go past these regions anyway. But the first thing you notice is sort of these things make about day periods and sub-day periods pretty easily if you just go about doing that. Okay. So as Paul showed, one of the things you might want to worry about is, are you putting in too much energy so you're changing the nature of convection? And you can sort of add energy to the flow up to the point until it becomes supersonic. And then you start shocking the gas. And then you shock the gas, you'd expect that to actually contribute to unbinding the star. And so here, sort of, for mass ratios up to about 0.4 to 0.5, you can stay sort of in the subsonic regime. And you should be able to sort of not broadly change the nature of the convection. Again, probably need simulations to actually see sort of the effect on the convective velocities and flows. The other thing too is that this is pretty sensitive to the time that you go into the CE, right? So the star is actually, the star is changing in time. The base of the convection zone is moving, and so that location where sort of convection is faster than orbital decay is actually changing in time. So there is some sort of sensitivity to it. We've run it up here. You get some sort of idea of the variability in that. So you need to sort of know sort of when the CE starts formally, when that dynamical plunge-in phase begins. Then I just want to say these are sort of conservative estimates. So first off, we've assumed the stars are not rotating. So if the gas is approaching co-rotation, then the in-spiral time increases dramatically. So then convection has even longer to operate, to carry energy away. What's also interesting here too is I think if you are in a vigorous convective zone and you're approaching co-rotation, you can't maintain co-rotation. So I don't know if one puts full-fledged convection into simulations, maybe that sort of slower phase there actually becomes faster, and you have more of a dynamical phase fully throughout than sort of this slow in-spiral phase. I don't know. Also, so we've assumed the convective velocities are unaffected by the orbital energy deposition. So if you add energy to it, then maybe those convective velocities increase, and then of course the convective transport timescale shortens, and so it's even easier then to carry the energy away. So I would say we're sort of conservative here. This is a fast talk, so there's nothing crazy about this, but sort of what I was thinking is, what are the effects, and if we incorporate this stuff into simulations, or if we incorporate it into population synthesis codes, what do we expect convection to do? So the first is just transfer orbital energy away to the surface and radiate it away, so it doesn't contribute to unbinding. That essentially means, I think, that the star just sits there. Its radius actually doesn't expand for a long time. It doesn't really expand until the companion gets all the way down to the center, and then you deposit a huge amount of energy very rapidly. And so it's like setting off a bomb at that point. So that's maybe one prediction of this. Now in theory, maybe you do put some into expansion, right? And so maybe you're not radiating all the way, some fraction of it's going into expansion, and the star can puff up a little bit. Okay, so this allows the companion to get much deeper into the potential well. So that's very interesting. That's how we get these sub-day periods. Yeah, and okay, and I said these other things, I think. It's very sensitive to time when the system incurs the CE. So there's nothing, this is a very, very, very simple argument. I would say so far convection is not in the simulations, so it could potentially help in some ways. Yeah, that's really all I wanted to say about this. So. All right, lots of questions.
I think I should talk about this at some point. Natasha's summary plot actually showed some of this.
Yes.
The figure she showed was actually including convection and radiation. And that's how you actually get into the slow spiral-in phase.
So in terms
slow
of
spiral-in phase. And that's the phase where, of course, all the energy that's transported by the in-spiral is convected, radiated away, which is...
Well, so okay, so I guess are you talking about in terms of the equation of state, or are you talking about the full convection in the
1D
simulation
pseudo
itself?
calculations.
1D pseudo calculations. Yeah, that's fine. Sure. Yes, Natasha.
They show exactly that behavior.
Okay.
Yeah, so I mean, this is why I said at the start of my talk, we need to separate the stages which we talk about, right? The slow
Yes.
spiraling is where the convection indeed carries over energy to the surface. Now, my problem is to understand how did you evaluate the role of energy intake during the plunge? Because whatever I see, I know that the time scale for the plunge is comparable to the initial orbital period. Now, initial orbital period is a dynamical time scale of a star. When you deal with the dynamical time scale of a star, it means that to carry energy by convection, you have to be in a sonic regime. So how you can carry that energy using subsonic convection, I don't understand.
Okay, so I guess I should back up and explain here. So we take the drag luminosity and equate it to dEdt. That in fact is mildly supersonic, right? It might be Mach numbers of a few in that regime there.
So your plunging was slowed down by significant amount.
The plunge-in, you can see it right here. Sort of, yeah, so the time scales for plunge-in are these curves up here. It's the standard thing people do with these. Now that, because it's supersonic, that's fine. It doesn't necessarily mean that the convective nature itself becomes
So
supersonic,
you
right?
start with subsonic, there's a time scale also to switch to supersonic. But what I'm saying is that you started already with a slow spiraling.
We start with whatever the spiraling is. So it's a Mach number of about, again, 2 to 4, essentially, Mach number. So yeah, so you plunge in a little bit from the surface, and then you enter this slow spiraling phase, yes. You are still supersonically shocking the gas in the area there.
Yeah, I mean, it's a standard
Yes.
slow spiraling simulation.
Natasha, I think maybe, and you tell me if I'm right, Jason, isn't
Sure.
the assumption that the companion is very low mass, so it takes many more orbits than if it's mass ratio 1 to 3 or 1?
Yeah, so
We didn't see that. I mean, when you plunge the low mass companion, it actually plunges faster than a massive companion.
What do you mean by low mass?
The mass ratio 10.
Yeah, so I was under the impression that you're talking about even lower things, like down to a Jupiter mass or something.
yeah, we are. But
Then
we go up
plunging
to.
even more faster.
I don't think
It's
you
just
can at a
close,
certain
yeah.
point.
It depends on whether the envelope expands in that phase.
Yes.
So the other thing I should
That's why
say
you get
here.
this counterintuitive
Yeah.
behavior.
So
I don't-
this is an estimate for sort of the answer. So you equate the drag luminosity to what's going on to dEdt
Yeah.
for the profile of the star itself. These are at sort of maximal extent. So whatever the initial primary mass is, we take the maximum extent of the star at that point in
So
time.
just to
calculate that,
clarify,
yeah.
your drag luminosity is released at the dynamical time scale or not at the dynamical time scale of the envelope? Because if it's at dynamical, you only can deal with supersonic convection.
No.
So-
So yeah. So it's moving in very slowly.
Okay,
So we're
it's
Keplerian going, moving in. Yeah. So it would be equivalent to
So it's
essentially, I think, what you're
artificially
calling.
created slow spiraling from the beginning, but it's not how it takes place.
But this is what you see, after your first decrease here, and then you enter this phase, right?
Yeah.
Yeah.
Let's have
But you're
that.
still in the convective zone, so I think these things still apply. I mean, the point is that you don't change the nature of the convection to something that's supersonic. So convection still operates much faster, even if you plunged initially and then you reach this phase here. If you have vigorous convective pot, you're still carrying that energy away as you're slowly moving through the star, orbiting and shrinking the orbit.
So maybe you
Yeah.
could clarify how you calculate your drag luminosity.
Mhm.
Okay, how's the luminosity, how's the energy from the orbit removed in your?
So you're putting it, so I'm assuming it either goes into the gas or it doesn't go into the gas. So it's sort of it's the Ostraker and 99 dynamical friction
How do
formula
you calculate
for.
that each time step? Just drag luminosity?
Yep, just drag
Oh,
luminosity.
so that
That's it.
convection doesn't change
Yeah.
much.
I think someone.
I want to ask a very different question, but actually very naive. Colin Norman keeps asking me this, but if this in-spiral phase lasts very long and there's not much happening, how many giants in our galaxy are doing this,
undergoing
and
this
can we
right
see
now?
an seismic signature of these events while they're going through, or timescales still long and fair?
Yeah.
But there should be some.
Well, if there is one pointish mass inside an envelope, does it change the other modes that it's calculated?
Yeah, I mean, so the time scale here is, these in-spiral time scales are something on the order of 10 to 100 years, or maybe they're a year to 100 years. So it's a typical in-spiral time, so the number of
So what
stars.
is this, 100 years?
So there should be 100 in the galaxy, but
Yeah.
not much.
Okay.
Kepler field is
Yeah.
only 1 in a billion.
Yeah.
That's correct.
Yeah, okay.
So it's gonna be hard to find something, but yeah.
If the features are big enough, we can do the Magellan clouds with Opal.
I mean, maybe you're gonna see these things, LSST or these sort of all sky surveys are the place to look, right? Because you'll see potentially the luminosities go up on some sort of timescales that are longer,
Yeah,
1 to
that's
10 year
couple of days status,
timescales.
right?
It is, and you gotta look at it over a year time or a few years timescales, but yeah, yeah.
Maybe one more question.
Yeah, I know.
So the next contribution we have is from Rosa Erickson, who talked about envelope structure and the application of drag pulling.
I hope those Make jokes about other people that I don't know, or will this all be recorded?
Oh, sorry, yes, I do, thank you.
All this is.
Yeah, but it's not good.
Well. Make jokes about no, without it being.
As long as you talk.
Alright.
We are.
I've been generous.
Okay, so I'm going to be talking about the application of the drag formalism, which many of y'all may be familiar with in some of Morgan's papers over the last few years, and how we've been working with it in our group and where we think it can go. So I think many of you have seen this before. It's just the qualitative picture of what's going on during in-spiral and some of the assumptions that come from this Hoyle-Littleton accretion framework have been used even in some of what we've heard about today. What you see in our little HLA box is this oncoming wind, which is going at the velocity of the inspiraling object, which is mildly supersonic, so we get a shock seen in gray in the cartoon. And then behind our embedded object, we get a wake of shock material that is the source of gravitational drag, which leads us to the in-spiral. And because of the symmetry, we get this vertical momentum cancellation in the back, which leads to a fairly high accretion rate. HLA lets us quantify how this process takes place based on some simple parameters. So we have the accretion radius, which we just we're actually working with. It defines the gravitational sphere of influence of the embedded object in the sense that it gives us a cross-section within which inflowing material is gravitationally bound or interacting with our object. The inflowing material has this speed v infinity, which just corresponds to the relative orbital velocity in the material. The mass flux that passes through that cross-section, m dot, is a function of the accretion radius, the density, and the speed. Due to the momentum cancellation, we say that m dot is an estimate for the accretion rate of the embedded object. And E dot is the kinetic energy per time of that material passing through. And because the shock is dissipating a lot of the kinetic energy, we use E dot as an estimate for the energy dissipation, which corresponds to our orbital decay. So in HLA, these quantities are intrinsically connected. It's super simple, but is this the right way to think about this problem? So when we look at realistic stellar models, one of our fundamental assumptions for HLA breaks down right away, which is the density structure. So it's easy to spot that stellar envelopes, even when they're expanded and low density, have a density gradient, but the question is scale. So if, for example, the cross-section of our in-spiraling object, RA, contains a substantial density gradient, then all the results that came from HLA have to be thrown out. As a kind of a cartoon example, these are MESA models. Let's say that our embedded object is about halfway in. RA is dependent on the relative masses, which in this case we call Q. So for low mass secondaries, which are in blue, maybe it doesn't matter because RA is really small. But for LIGO type systems, more like what's in green with a higher Q, the density gradient becomes pretty important to incorporate because through our accretion radius, we have something substantial. So first, to generalize this type of density structure for the purpose of numerical simulations, I want to define these dimensionless quantities that relate to the familiar ones, Mach number and a dimensionless density gradient epsilon rho, which is simply a measure of how many local density scale heights fit in the calculated area at that separation. But for reference, if epsilon rho is 0, we have no density gradient, it's just HLA. And for epsilon rho of 10, we have a very steep density gradient. So we'll have a look at what that means. So in this plot, we relate the old with the new. So you can see sound speed and rho on the top, and then Mach and epsilon rho on the bottom. From the limb, which is on the outer edge, to the core, which is closer to me. Essentially, density features are shared between the two of them. And what I want to point out is that something that appears really subtle in our traditional quantities actually gets blown up in these dimensionless quantities. Also, something else that you can't really see, but which is also true, is that at least in this particular case, you can see that epsilon rho is never lower than 1, which is to say throughout the whole envelope, at least for this case, it counts. So when you run numerical simulations that use these Hoyle-Littleton boxes and these quantities that we've applied, you get a really different morphology from HLA. So it's not symmetric. So on the left, we have the HLA version. Epsilon rho is 0, symmetrical shock. But even with a relatively minor density gradient of 0.3, all the symmetry is broken. We lose the momentum cancellation. Accretion is suppressed, not to mention at higher values. So the clean connection between drag and accretion that we saw in HLA no longer applies. So for each of those simulations, that was just a selection. They're specified for a Mach, an epsilon rho, a Q, and there's a corresponding drag coefficient CD, which quantifies how different the average drag force is from that predicted by HLA. So here we have plots of CD against epsilon rho and Mach, also across axes of gamma and Q. And the drag force computed in the simulations increases with increasing Mach, epsilon rho, and Q. So what this means, given an epsilon rho of greater than 1, so I've sort of grayed out this area, is we'll often get a faster in spiral than HLA would predict, which also impacts things like total accretion, since there's just less time to do it in. So structure matters in helping us better predict our final outcome. So I want to apply this new drag formalism as broadly as possible, but what do I do? So from the simulations, we got the drag coefficients for given Mach, epsilon rho, and Q. All that remains is to simulate the relevant parameter space of Mach, epsilon rho, and Q to tabulate the drag coefficients, much of which has actually been done in these papers listed, and then we can create an interpolation function between these related quantities, and then we can apply these to any stellar profile you want. So you can use a 1D stellar profile, incorporate our drag coefficients, and integrate an in-spiral, but we can keep going. So from the 2017 paper came a fairly simple relationship between epsilon rho, Q, and Mach number, which in the case of a polytropic envelope says if we have 2 of those quantities, we have the third. So maybe we can simplify how we get our drag coefficients, but first we had better check and make sure that the drag formalism actually applies across the populations we care about. So I'm going to skip over this. We know what population synthesis people care about, like when they're looking at binaries that go through CE, and we're actually further complicating this by adding in structure, but let's do it anyway. So I've applied this formalism to several libraries of realistic stellar models that range from 1 solar mass to 90 throughout the giant branch. I was agnostic in my spread, but what this means is it's pretty biased towards high mass stars, so keep that in mind, since my group tends to be more interested in LIGO type binaries. I was originally looking for where the formalism no longer applies. So looking at this big range of masses, we see a wide variety of late stage structures. On the HR diagram, you can see that for any given particular size, at these different masses, you're just going to get something really different. So originally, I'm just saying that this is the Wild West. What is this going to look like, and how far can I stretch this? If you look at the diagrams on the right, we're looking at one particular radius for the spread of different masses. We have all sorts of different equations of state in the envelope. Some are more polytropic than others. But more importantly, they look different, right? So you would expect things to be different. But let's look at some of the relationships we care about. So these are some of those quantities coming back to haunt you. So together with the mass ratio Q, Mach and epsilon rho all create this sort of three parameter space. For any envelope, we can make a track through this parameter space using all these three. So it goes from the outside in. All right, so this is going to be our core boundary, and we're stopping at about 95% of the total star's radius because I don't want to mess with onset right now. So we already are embedded. We look at our two key quantities for an envelope of a 6 solar mass star as it increases in radius, and it has a 1.2 solar mass neutron star. And then we go up to 100 solar radii, 250, and 400. And though the envelope is evolving, the tracks are confined to a pretty small range of the parameter space. So now let's add another axis. This is mass increasing from top to bottom. As we go through our library, you see some subtle differences, mostly related to how the equation of state is changing in certain regions. But even with a system like 3 solar masses, which is more for like white dwarfs, it's still staying confined within this pretty small range of the parameters. Extending to another axis, which is going across Q now, we get these beautiful self-similar fans. Now, although these stars are not polytropes, I still want to use the polytropic formalism included in the 2017 paper to see how self-similar they are and how close to polytropic they are. So this relation is the general version, but when you use a Keplerian orbit, which we are in this particular case, and assume it's polytropic, you end up with this very nice quadratic, which I'm going to call epsilon rho q, which is to say if these fold up in a very polytropic way, it should just look like a nice quadratic. So let's see. So here it's the same binary systems, but looking at epsilon rho q instead of epsilon rho, and two things pop out. So first, yes, they're self-similar, but they also seem to truncate around the same place, even though we didn't cut off our radius based on these quantities. So this pointed me to the possibility of maybe being able to parameterize this curve. So this is the whole library for expanding radius. So this doesn't include pulsations, but it does include every expanding radius, which is to say our initial common envelope onset separation. The same relationship holds across all axes. What you see is each dot is a simulation that Morgan and his collaborators have done. So each one of these points to a specific drag coefficient, which can then be used to actually take these tracks and integrate an in-spiral. Note that even across this huge range, so this is all the masses and all the radii up to R max, the curve on the right is still pretty truncated, meaning there might be common limits to these values during in-spiral. So not only is this still relevant across the whole stellar population we care about, but it appears we might actually be able to describe these key dimensionless quantities in a prescriptive way, which came as a surprise to me. So as a first application, just to show you what we'd like to do with this, this is a particularly dramatic example of an in-spiral integration that looks different in HLA than it does using the drag formalism. So on the left we have the HLA, and on the right we've used CD. And it's clear that they don't evolve in the same way. So for example, here we see that we're sort of going over the same ground many times. In fact, our formalism material, on the right we have this very quick plunge in. There's more work to do to try to understand the conditions under which common envelope ends, but already this has implications for things like final separation beyond the energy constraints of the alpha formalism, or maybe transitions between dynamical and self-regulated phases. So we're getting started now exploring just that, especially as a comparison for in-spiral trajectories seen in, for example, 3D hydro simulations. So I'll conclude with that, and I'll take any questions.
That's your last point. Is there a way within this formalism to sort of choose where you can start? I mean, because the initial plunge dramatically changes the outer structure, and it doesn't seem like it should be applicable there. But where do you link up the two?
Right, exactly. So our assumptions are that we are already embedded, and I'm trying to sort of avoid the messiness of onset. Something that I've definitely learned today is that something we should maybe take into account. But as far as the limitations of where this does apply, it needs to be dynamical, meaning that we're always moving into undisturbed material. And if, for example, onset does pull up and disturb more deeply into the star, then yes, we would have trouble applying it.